Hi folks, welcome. For today's material, I figured that we'd start off by looking at a particular theorem here. This is something that I pulled from isosceles triangles here, so we can take a look at this. So we're told that in an isosceles triangle, the medians drawn to the legs of the triangle are congruent. Okay, so as always, in order to do this proof here, we want to set it up first, right? We need to figure out what it is that we know, what it is that we have to show, our givens and our proof here. Now, normally, if this were a conditional statement, it's very easy for us to deal with that because everything in the antecedent will be the givens and everything in the consequent will be goals. Unfortunately, we don't have that here. But it's pretty easy here to convert this into a conditional statement. It's pretty clear here that the congruency of the medians is going to be our goal. We want to show that the medians that I draw will be congruent to one another. And we're mentioning that we start off with an isosceles triangle here, and the medians drawn to the legs of the triangle. So that means we need to have an isosceles triangle, we need to have medians drawn. So basically what we can do here is we can set up something like that here. We can always set up that thing here. So if you were to actually set this up, please try to set it up first before you proceed with the video. Try to see what this looks like here, and then we're going to talk about how this proof is going to be done. Okay. So when you set this up, it should look something like this here. Okay, so we have something that looks like this, where you have your isosceles triangle, so that's two sides congruent. Now note that since this is an isosceles triangle here, we can actually designate which two sides are congruent. So even though technically it's not given to us which sides are congruent, I can create them, and we're given some medians here. So our goal is to show CD is congruent to BE. Okay, so I'm going to go ahead and mark the pieces that we know. I want to show CD and BE are congruent here. We're told that AB is congruent to AC. And we have CD and BE being medians. Now, if you remember medians here, ladies and gentlemen, medians, remember that medians hit midpoints here, so D and E are going to be midpoints, and therefore these are congruent here. So it's pretty clear that we're going to be dealing with congruent triangles. However, what's not clear is what the triangles are, because unlike the previous cases where we've looked at these sorts of things here, our triangles, there seem to be a lot of different triangles here. In particular, you have, like, for instance, ABC is a big triangle. You also have ADC, you can have AEB, you can have DBC, you can have EBC here. And, if we include this middle point here, where the two medians intersect, everything else is going on here. So a lot of times what's going on here, if you have a picture like this, sometimes it's a good idea to sort of like pull the picture apart, right? We want to see which pairs of triangles here will work out. And it's difficult to see them because the triangles are sort of on top of each other overlapping. So we want to try to see what's going on here. Now, there are two ways you can tackle this problem here, and I'd like you to think about them. I'm going to do one way in this particular video here, but you may want to see what would happen if you tried a different method here. I see here this triangle ABE and this triangle ADC here. These two triangles certainly have the two pieces that we want here. It may not be obvious why they're congruent here, but we can kind of figure out what, we can try to figure out what's going on with that. And, excuse me, if you're having trouble figuring out why they're congruent here, perhaps it's a good idea for us to sort of pull the triangles apart. I mentioned this earlier. We can try to draw the triangles separately and see what's going on here. So let me go ahead and do that. So my triangles are going to look like this here. Oh, darn. The crease in the notebook underneath it, unfortunately, has done that here. Okay, so here's A, here's E, here's B, here's A, here's D, here's C. Okay, so we know AB is congruent to AC here. Notice that both these triangles share angle A on top, so we can mention this here. That's going to be a thing. And again, BE and DC here, we do not know anything about them, so I'm just going to leave them to the side for the time being. AE and AD here, well, notice that both of these happen to be halves of what you're looking at here. This is half of AC, this is half, AD is half of AB here, and both of them are congruent. So it makes sense that if we have two congruent things and we split them in half, they should also be congruent as well. So it looks like here we're going to use side angle side in this upper pair of triangles here. You can also do the same with triangle DBC and triangle ECB here. It's going to be the same idea. You can always set it up that way as well. So it turns out here what we're going to have is going to have this here. We're going to have side angle side here. And then once we have side angle side, we can put it all together. So now this is where the actual proof comes into play here. So I'd like you to try the proof out as well. But again, we're going to go through the proof, and I'm going to write this out in paragraph form. You can very easily convert this to two-column form if you so choose. Okay, so in this situation, let's go ahead and mention this here. So it turns out the first steps are pretty easy, right? So I'm going to mention this here. So first off, we're going to be given the AB, right? We are given that AB is congruent to AC, and that's a pair of sides. And we know by the reflexive property angle A is congruent to itself. Notice I'm using angle A because it's unambiguous which angle A I'm talking about here, and that's a pair of angles. Now this is where the last pair of sides comes into play, and it's a little bit tricky here, but it's very doable. Right now we have to follow sort of a specific motif when it comes to these sorts of things here. Let's just run through that, okay? We are also given, so we can mention also given that CD is a median to AB, and BE is a median to AC, right? So now we can use the definition. We know what a median does here. Median intersects the opposite side of the midpoint here. So we can use the definition. By definition of median, we know D is the midpoint of AB, and E is the midpoint of AC, right? By definition of median here. Now, note that we're not going to use the standard definition for the midpoint here. We're instead going to use the halves portion, right? We know a midpoint does something to a segment here. Not only does it split a segment in congruent pieces, it also creates segments that are half as big as the original. So I'm going to mention that here. Since the midpoint of a segment divides that segment into parts half as long as the original, right? So we can just mention that. That's our theorem here. We can mention this. We have AE is 1/2 of AC, and AD is 1/2 of AB. Now note that we've established this fact here. We also have established previously that AE and AD are congruent to one another. So we should be able to put this all together. And therefore we can continue with this here. So note that we're splitting something in half here. We're splitting congruent things in half, so we should be okay. So, this is our division postulate here, but I'm also going to establish this fact here. We notice that we have congruent things, so I can just mention that. So we can say since halves of congruent segments are congruent, AD is congruent to AE. And that's my last pair of sides. Phew, that's a lot. We did a lot for this pair of sides here. So thus, by side angle side postulate, triangle AEB is congruent to triangle ADC. And now we're basically done here, because now all I do is show the last two pieces congruent. Thus, we can say BE, or CD is congruent to BE, since corresponding sides, or corresponding parts, of congruent triangles are congruent. Now note that you can do a very similar proof, by the way, for the lower pair of triangles. If you decide to use triangle DBC and ECB, you would also done much the same thing. You would have you would use the reflexive property and this halves thing again, and then you would use a pair of angles. You'd still use side angle side, just be slightly different here, but it all works out nevertheless the same. And and again, for practice, you may want to see what would happen if you tried to do it using the lower pair of triangles. Okay.